Well, hello and welcome once again to Onco Physics. Today what we want to do is take a look at something called rotational dynamics. And what we're going to look at today is specifically how we do kinematics with rotational dynamics. Up to this point, we have studied Newton's laws, we've studied kinematics, we've studied all kinds of things, but we've studied them mainly in a linear sense, right? The object that was in question was traveling either in a linear path or a curved path, okay? But it was not spinning, okay? And that's what this unit or this chapter is really all about. It's about objects that are spinning about their own axis. And to try to make that a little bit more clear, in the picture that we have down here at the bottom, let's see here, down here, in this picture down here, what we've got is we've got an object that has a center of rotation right here, right? And here's our object out here, okay? The pencil there. All right, here's our object. Let's do that in black. Here's our object right here, and our object is being twirled around in a circular path like this, okay? The object itself, right, this object itself is not spinning, okay? It is being rotated about a central point, but the object is not spinning. The axis of rotation is outside of the object, okay? So this could be my hand here, and this could be say a rope, and this could be some sort of a bucket up here, and I could simply be swinging it around, right, above my head, or swinging it in a vertical sense. But that would be circular motion, right? The object would be going in a circular path. What rotational dynamics is not necessarily something that's going in a rotational path, but something that is spinning about its own axis. And you could think of taking a basketball. I can't do this because I'm not that talented. But you could think of taking a basketball and putting it up on your finger and spinning it and trying to hold it on your finger, right? The ball itself has no translational motion. Translational would be linear motion, but it does have spinning motion. It is spinning about its own axis. That's what we're trying to take a look at in these next few videos. If we look at the top picture up here, what I've drawn is I've drawn two circles, and those circles represent two wheels, okay? And the wheels could have tires on the outside. So they're rubber wheels, if you will, like on a bicycle. And up at the top, we have a dot that represents just some point on the outside of the wheel, okay? And what would happen if I took my wheel, all right, and I started rolling it so that I rolled it through some angle, and now my dot is over here at this position, okay? Well, my wheel has a radius, and this radius is shown by denoted by the red line there. So that's my radius. It has a center point, okay? Right? And what I've done is I have rolled my wheel from a point up at the top over to a point on the side, and there's definitely some arc length that my wheel has rolled through. Right? So there's an arc length on the outside of, or the circumference of the wheel. I have also rolled my wheel through some angle theta. Okay? And in rotational dynamics, instead of dealing with lengths in meters, right, we're dealing with things that are spinning around, and as things spin around, they go through some angle, okay? So my wheel started at the top point up here. It is now at this point over here. My wheel has gone through some angle theta, and it looks like it's about, it's about 90 degrees, okay? One of the other things that we have to get used to in rotational dynamics is not just that we're dealing with things that are spinning about their own axis, but we're no longer going to be dealing in degrees the way we normally think about, or angle in degrees. We're going to be thinking about angles in radians, okay? we all have our calculators, and usually our calculators are set to angles in degrees, right? Now we have to think about degrees in terms of radians, okay? And it's an easy conversion back and forth from one to the other. Let's say if I have a circle, how many degrees and radians do I have in one circle? Well, I've got 2 pi radians in one complete circumference of a circle, right? Well, how many degrees do I have in one complete circumference of a circle? Well, I've got 360 degrees. So I have this equality that I can use to go back and forth between radians and degrees. So let's say, for example, that I've gone through 90 degrees and I want to know how many radians that is. Well, I know that I have a relationship that 2 pi is to 360 degrees as some number of radians, theta, is equal to, say, 90 degrees. And I want to figure this out. Well, through proportions, we can figure this out. Now, you may have another way of doing this. There are many ways to do this, and you use whatever way you're familiar with and whatever way works for you. This works for me. So now if I want to figure out how many radians I have in 90 degrees, what I do is I'm going to cross multiply. So 90 times 2 pi is equal to 360 times theta. I divide each side by 360 and I get 90 times 2 pi divided by 360 is equal to theta. And if I do that on my calculator, what I get is about 1.57 radians. All right, that's how many radians is subtended by this angle up here. All right, 90 degrees is about, or not about, is 1.57 radians. Okay, now there is a way to go back and forth between degrees and radians, right? There's also a way to figure out how much of this arc length that I have. Well, we know that if I have a circle here, all right, there are 2 pi radians in the circle, okay? If I want to know what the circumference of the circle is, all right, I want to know the length from, say, this point and going all the way around, going back to this point again, right? It's 2 pi times the radius of the circle, right? That's what will give me the circumference of the circle. Well, if I want to know any part of the arc length, right, which is sometimes denoted as x, is sometimes denoted as s, all right, I can get that with the relationship that 2 pi times r, right, is equal to x or is equal to s. Okay, so basically, if I want to generalize this, this is the angle that we went through. This is the radius. So theta times r is equal to x or s, depending on what variable we like to use. So that's one of the relationships that we can get. We can figure out just how far we've traveled, right, on the outside of the circle. Now, taking that just one step further, think of yourself on a bicycle. What happens when your bicycle rotates, right, your wheels rotate from this position to this position? Does your bicycle stay in the same linear position? I hope not, unless you're cycling on ice, right? As long as you have some traction, you have some friction, your bicycle, right? If this is your bicycle and your bicycle wheels, it's going to travel from some position A to some position B. So you're going to have some linear motion of the center of your bicycle wheel from this point to this point, right? If you were standing there observing, you would see the center of the wheel move from point A to point B because your bicycle wheel actually started rotating. How far does your bicycle wheel actually move? Well, if your tire rotates one entire revolution, which would be 2 pi or 2 pi radians, right? So the circumference of the wheel would have traveled 2 pi times your radius, right? And so your bicycle would also have traveled, as long as there's no slippage, your wheel, the center of your wheel, would have traveled the same amount of displacement that the outside of your tire did, right? So this value here, this x or this s, doesn't just give you the arc length that your wheel traveled, right? It also gives you the linear distance from a point A to a point B that your circular object, whatever it might be, traveled as well. Okay, so that's something to keep in mind. All right, so I just showed you one of the relationships between the angular or rotational dynamics and the linear world, right? In rotational dynamics, the angle times the radius of our object, whatever that object is equal to the linear distance that something may move, or the arc length, depending on what you're looking for. This is one of the relationships. There are a whole lot of other equalities that we can have, and this is a table of them. If you don't already have this, you can go onto my website and you can print it out, or you can Google rotational dynamics equations, and you'll find this pretty easily. And what this table does is it shows us all of the variables and the equations for kinematics that we're used to in this column, right? And it then gives us the rotational counterparts in this column, right? And then we have a nice column of equations over here that gives us a connection between the translational and the rotational variables. Remember, translational means that I'm traveling in a line from point A to point B. This is translational motion, right? Rotational motion, right, is something that is spinning about an axis, okay? But it's important to remember too that we can have both translational and rotational motion going on at the same time. For example, if I have a bicycle wheel, right, and it's spinning, right, it's spinning about a center axis going through the wheel, right? It's spinning, say, in this direction, so it's spinning in a clockwise direction. My wheel is going to move in that direction as well. The center of my wheel will move in that direction. So as it's spinning, it's going to move from point A to point B. So you can have both translational and rotational movement at the same time. So let's look at some of these connections. The first one is one that I've just mentioned, and that is the relationship between x, right, linear displacement, and theta, which is an angular displacement, right? And the relationship is x, or sometimes we use s, the letter s, is equal to r, the radius, times theta, or the change in theta, okay? We also have a relationship between linear velocity and angular velocity. If an object, like a wheel, is spinning about its own axis, that object can be spinning quickly, it can be spinning slowly, it can be spinning not at all, right? And so that rate of spin, if you will, is the angular velocity, okay? If I want to go back and forth between linear velocity and angular velocity, it's a very similar equation to the first one up here, right? And the variable that equates them is the letter r. Linear velocity is equal to the angular velocity times the radius, right? And then we find the same thing down here for acceleration, right? Linear acceleration is equal to the radius of the wheel, or whatever it is we're talking about, times angular acceleration. Okay, so we have the same variables, but in the rotational sense, they're for things that are spinning around. Okay, so let's go back up here to the velocity. So the velocity here, right, the linear velocity would be, say, for a point on the circumference of the wheel, right? I want to know how fast this point takes to go from here all the way back to here again, right? Well, that would be the linear velocity. If I know the angular velocity and I know the radius, it's very easy to get the linear velocity of that point. Also, if I want to know how fast my wheel is traveling, say from point A to point B, that would also be the linear velocity from this point to this point, if I know the angular velocity of the wheel. So there's a lot of back and forth, and there's a lot of things that we can figure out. Well, just like in kinematics, where we had our favorite equations, and they call them the big five, and honestly, we probably use some more than others, right? So this is a favorite, right? This is certainly a favorite, especially when we come to projectile motion. This one's a favorite over here, right? So we use all of these, right? Some more than others, and they have their counterparts in rotational dynamics, right? So for linear velocity equals initial velocity plus acceleration times time, well, angular velocity equals initial angular velocity times angular acceleration times time, right? The equations are the same exact form, right? We just replace the translational or linear variables with the rotational variables. No difference, okay? So let's do an example using our newfound equations. I don't want to move this down too much. I want to try and keep this on the screen. So let's say that I've got a wheel. There's my wheel. It's got a radius equal to 0.5 meters. And it is initially at rest. Okay, so omega initial is 0 radians per second, right? And through some means, I increase the velocity of my wheel, right, from 0 up to 12 radians per second. Right, so it is now spinning. Right, let's say it's spinning in a clockwise motion here, and I'm able to do that in a time equal to 3 seconds. Okay, so I would like to know a couple things. One, I'd like to know what my angular acceleration is. Well, to get angular acceleration, I can use this equation up here, right? V final equals V initial plus A times T. But I'm going to use the counterpart over here. Omega final equals omega initial plus alpha T, right? But I want to solve for alpha. So if I have this equation, omega final equals omega initial plus alpha T, right? If I subtract omega initial from each side, I got omega final minus omega initial equals alpha T. I divide each side by T, and I get omega final minus omega initial divided by T equals alpha. I can now solve for alpha. Well, so I've got 12 radians per second minus 0 radians per second divided by 3 seconds. And what I get is, 4 radians per second squared. That would be my acceleration, my angular acceleration. All right, let's say that I also wanted to know in the time that this thing spun up to 12 radians per second, I'd also like to know how many radians we spun through. Okay, well, which equation would help us here? Well, the first one's not really going to help us because we don't have an average velocity, all right? This one's not going to help us because I'm looking for theta. See, here we have an equation that has theta, initial velocity, which we know is 0, time, which we know, and acceleration in time. So we could use this equation right here, right? So theta is equal to 0 times time, which was 3 seconds, plus 1/2 alpha, which is 4 radians per second squared, times t squared. Well, t is 3 seconds. Running out of room here. Squared. All right. So this goes out right away because it's 0. All right. And theta then is 1/2 times 4 is 2 radians per second squared, times 3 squared is times 9 seconds squared. The seconds cancel out. All right. And 9 times 2 is 18 radians. That's how many radians that the wheel will have spun through in those 3 seconds. Well, I'd like to know one more thing. I'd like to know what the linear distance, say my wheel traveled, it spun, right? Let's say I allowed it to spin on the ground. What's the linear distance that my wheel would have traveled if it was on the ground? Well, remember that I have my equality, and let me go back up a little bit here. All right. Here's my equality equation right up here. X equals r times theta. All right. So, oops, a little too far there. So x equals r times theta, which is equal to the radius, which is 0.5 meters, times theta, which was 18 radians, and 0.5 times 18 would be 9 meters. Okay, so that's the distance, the linear distance that my wheel would have traveled. I hope that helps as far as learning a little bit about kinematics in a rotational sense. I'm going to be doing a whole lot of examples, so look on the YouTube channel or my website for those examples. Hope this helps and have a great day.